Hello everyone, welcome back to Mysore pathshala. I am Pooja Vaishnav and today again we are going to start with the third lecture of chapter solutions. So in this session we are going to discuss what is vapor pressure, what is Raoult's law, ideal and non-ideal solutions. And this session is going to be very simple, easy to understand. So without making any delay, let's get started and I want you to watch till the end without missing even a single topic. So let's move on with our first topic, what is vapor pressure. So concept is very simple. We know what is vapor and what is pressure. Both of the term. Just join it. It's a vapor pressure. Just consider you have a beaker and it's filled with the water. And you are supplying some heat over it. And when you supply heat, we know that water molecules converts into vapor form. Right? And just consider you have covered this with the lid. You have completely covered this beaker with the lid. So what happens? This vapor which is converted, the water which is converted into vapor, they are going to move up and they are going to collide with the lid. And what happens? They'll come back and they creates a vapor pressure on this surface. We had a surface, right? And if you consider this is a water surface, the pressure created by the vapor on the surface is called vapor pressure. Simple. The pressure on the surface of liquid which is created by the vapors itself, they are called vapor pressure. Simple. And generally when does this occur? In equilibrium stage. Right? So what are the factors which affects? Nature of liquid. Consider a liquid or a solution which is having, we know that all the solution is made up of components, right? Either it can be solute and solvent. We have already discussed about this, right? If the components are having very much attractive, if they are having strong force of attraction, so we'll take two cases here, okay? Case 1 and case 2. In case 1, consider the components which is present inside, they are having very strong attractive force. So when they are very strong attractive force, they won't convert into vapor form easily. So if the vapor is lesser, then the pressure created by the vapor is also lesser. So can I say, if the intermolecular force, that is IMF, intermolecular force of attraction, is higher in the liquid, then the vapor pressure is lesser. So higher the intermolecular force of attraction between the components present in the liquid, decrease in vapor pressure is observed. Simple. Case 2. If the intermolecular force of attraction, if the attraction is very much lesser, then they'll convert into vapor form easily. And once when they convert into vapor form, then the vapor pressure also increases, right? So vapor pressure increases if the intermolecular force of attraction is lesser, and it decreases if the intermolecular force of attraction is higher, right? So intermolecular force of attraction plays an important role over here. And next, how about temperature? I told you, if I increase the temperature, I am supplying temperature here, right? If I am supplying heat, it means the temperature is increasing. If there is increase in temperature, what I observed, the vapor pressure also increased, because look, here we have particles, right? When I supply heat, these particles gets more energy. They are more excited. When they get energy, they'll try to escape and convert into vapor form. So if I keep on increasing the temperature, more molecules, more particles are going to convert into vapor. And if there is more vapor, then more pressure is created. So higher the temperature, higher is the vapor pressure. Higher the temperature, higher is the vapor pressure. Simple. And next comes pressure of impurities. Let me rub this thing. Pressure of impurities. Look, impurities can be volatile or it can be non-volatile form. And do you know what is volatile and non-volatile? Okay, let me tell you what is volatile and what is non-volatile. Again, consider the impurity is volatile, and in one more case it is non-volatile. What is volatile means? They convert into vapor form easily. They convert into vapor easily. And non-volatile means they won't convert into vapor. They won't convert into vapor form easily. They won't convert into vapor form easily. Okay. So suppose if the impurity is present in a liquid. So this is a liquid. Okay. Consider we have a liquid water. Okay. And we have impurities. Impurities considered as any other liquid considered as ethanol. They are present in very small quantity and I will consider them as impurity here. Okay. If they are volatile, if this is volatile, and we know that ethanol is also volatile, and if this is volatile, then they convert into vapor form. We have water vapor already. Right? So we are having vapor here already because of water. And if this volatile impurity is also contributing in vapor, it means the total pressure due to vapor is also increases, right? So what happens if the impurity is volatile? Vapor pressure increases. If the impurity is volatile, vapor pressure increases. If it is non-volatile, it means it doesn't convert into vapor form. And if it doesn't convert into vapor form, then there is no more pressure. So vapor pressure decreases. Simple. If the impurity is volatile, vapor pressure increases. If the impurity is non-volatile, vapor pressure decreases. Simple. Now let us move on to our next topic, Rolle's law. What is this law? This law is very simple, but if you understood, it's going to be super duper easy. Okay. Look, I'll just share you one story or something. Consider it as a story. Okay. Consider you went to a trip. Okay. You went to a trip and your teacher said you're going to carry a money to spend for anything during the trip, but the condition is how much amount you have bought, that much only you can spend. Suppose there are two friends, Arav and one more is considered as Bunty. Okay, these two are friends, Arav and Bunty. Arav bought 600 rupees and Bunty bought 400 rupees. And the teacher says, already said, how much ever amount you bought, that much only you are going to spend. Not less than that, not more than that. It means Arav cannot carry or cannot lend money. He can't ask any of their other friends to give money and spend. That's a condition. What teacher said? You are not supposed to spend a money more than what you bought or less than what you bought. It means Arav need to spend 600 rupees completely. He couldn't take extra money from anyone, or he cannot spend less than what he have. Similarly, Bunty bought 400, it means he is going to spend 400 rupees. Together, the total amount here is 1000. Right? So these both are friends. Right? As I said, Arav and Bunty are friends. Together, it's 1000 rupees. Correct? So, here the statement, if it is followed, then it is Rolle's law. Simple thing. Here the same thing. Consider A and B as a component of a solution. Here I am just relating this concept with the Rolle's law. Consider this Arav and Bunty. They are two liquid components. Okay, and after mixing totally. Okay, I'll explain this concept first in a form of liquids in a solution form, and then relate why I have explained this topic. Okay, look, I have taken two liquids, liquid A and liquid B, and initially they were in separate beaker, right, and they are covered as I said, and obviously if they are covered there is some vapor pressure will be there, both will be having some vapor pressure. So what I will write, the vapor pressure present here is going to be considered as PB naught, and the pressure here over the A component is PA naught. Okay, it's a vapor pressure in its pure form. They are in pure form, right? Obviously they are in pure form. Now once when I mix them A plus B, so again this is covered, but here A and B both are mixed completely. Both the liquid are mixed completely, right? So now this is a solution and it's covered now. Now what happened? Here we'll have a vapor, and the vapor present over here, the total vapor pressure present over here is due to both component A and component B. And what does this statement says? It says the pressure, the partial pressure, the pressure due to A is directly proportional to its mole fraction. It means if I have A component more, then the pressure due to A is also more, and if component B is more, then the pressure due to B is also more. Simple concept, right? If A is more in a liquid, then they converts into vapor easily and the pressure due to that is also more. And if B is higher in amount, it means the pressure due to B is also higher. Same thing they are saying in a statement. The vapor pressure of each component solution is directly proportional to its mole fraction. So they are considering its mole fraction. They are saying in terms of mole fraction. Okay. So the partial vapor pressure of each component is directly proportional to its mole fraction. So can I write P is directly proportional to mole fraction for a component A? Similarly, PB is directly proportional to mole fraction B. So what is this PA and PB? They are partial vapor pressure. Why I am calling them as partial vapor pressure? PA and PB are called as partial vapor pressure. Partial because now they are in mixture form. So partially A component is present in total vapor pressure. Partially B component is present and they are contributing in total vapor pressure, right? So this is the reason why we are calling them as partial. Okay. So partial vapor pressure of A is directly proportional to mole fraction of A. Partial pressure of B is directly proportional to mole fraction of B. And the question is, ma'am, why you have related this and this? Simple thing. I said statement. Instruction given by a teacher. What she said, the amount which you have bought, that much only you are going to spend. Means 6. If Arav is there, he should spend 600 only. So the amount of spending by A is directly proportional to its amount what he bought, right? Similarly, the amount which is bought by Bundy is directly proportional to what it spends. So higher the amount of Arav, higher is its spending. Lower the amount of any component, lower is its spending, right? So that's a relation I have just related. Okay. So I hope you have understood. The higher the vapor pressure, it means higher is the mole fraction of that component. Higher is the amount of that component present in total liquid. Okay. So now can I convert this into this form? PA is equal to PA naught XA, PB is equal to PB naught XB. Okay. This is somewhere you can write it as X, and in some textbook it is like this. So it is chi. Okay. I'll just say it as X. It's easy to pronounce, right? Okay. Now the total vapor pressure of solution is PP is equal to PA plus PB. Yes. So total vapor pressure is due to both the component A and B. So I'll write it as PA plus PB, and PA is equal to P naught XA, PB is equal to P naught B XB. And if I rearrange this, I'm going to get one more equation. And this equation we got by one of this concept. One more important part here. XA plus XB is equal to 1. So mole fraction of A and mole fraction of B is equal to 1. Mole fraction of A plus mole fraction of B is equal to 1. So this is one important part over here. And in vapor phase we have one more equation. Pa is equal to XA into P total, Pb is equal to XB into P total. What is Pa? Partial pressure of A component. What is XA? Mole fraction of A component. And P, what is P total? Total vapor pressure in solution. Similar case even here. Okay. Now let us move on to our ideal solution. Okay. So what is this solution again? Look, we have many different types of solutions we see in our daily life, right? Suppose you have you went to one party. Okay, you went to a party, and the party is one of your friend whose birthday party it is. So in that party they have arranged one drink, one juice. Okay, and that juice is made up of, by mixing two components they have made. Okay, consider it as water and ethanol. Okay, and now I'll say this is okay. Yeah, let it be as water and ethanol only, and I'm going to say this as an ideal solution. Why I'm going to say this as an ideal solution? Because it is following one rule. And what is that rule? That is Raoult's law. And we know that what Raoult's law said. Raoult's law says the partial pressure of components is directly proportional to its mole fraction. This is what he said, right? Okay. Now let us see what is ideal solution. Okay. So we have, consider you have a solution. Consider you have one solution with you. Consider you went to a party and you are having one. They have given you a liquid mixture. Okay, to drink. And suppose that is made up of two components, A and B. Okay. And as this mixture is made up of two components, I'll take it as in a separate form also as A and B. This is A component and this is B component. And after mixing this two, I got this new mixture. And obviously, in liquid A, there will be an interaction between AA molecules, and in liquid B, you will be having an interaction between BB molecules. And after mixing, you will see an interaction of A and B, right? So if the interaction means the force of attraction between them, if it is same, if even after mixing, if AB interaction is equal to AA and if it is equal to BB, then such liquid mixture is called ideal solutions. So I will call this as ideal. And we have few more conditions, not just this. It should follow Raoult's law also. And what does the Raoult's law says? Partial pressure of a component is directly proportional to its mole fraction. So this is also being followed. And after mixing, you will see there is no change in volume. It means suppose you have taken 10 ml of A component and 10 ml of B component, and after mixing it should be 20 ml, right? It means there is no increase in volume or decrease in volume, you will observe. So there is no change in volume, there is no expansion or contraction on mixing is observed, and there is no energy evolved or absorbed. You will not see any change in energy. Even after mixing, the energy present here, here and here is going to be same, completely same. Okay, so such solutions are called ideal solution. And the question is, do we have ideal solution in real? Ideal solution, 100% ideal solution doesn't exist. But yes, there are some solutions which behave ideally. So here we have some examples given, like benzene and toluene. When I mix them, they act like an ideal solution. It means their interaction will be same. They are going to follow Rolle's law. There will be no change in volume and there will be no change in energy observed. So similarly, hexane, heptane, ethyl iodide, ethyl bromide mixture, chlorobenzene and bromobenzene mixture. So these are the examples of ideal solution. Okay, ideal. And what does this diagram shows? Okay, look, just we have drawn a graph between vapor pressure versus mole fraction. Okay, vapor pressure versus mole fraction. This is what mole fraction is, right? So initially, let us suppose I'm drawing a graph only for component A. So what is happening from this end to this end? Mole fraction of A is increasing. Mole fraction of A is increasing. Okay. So 0 to 1. So what happens at this point when the mole fraction of A is 0? Okay. So the vapor pressure here is going to be there. Do we have any vapor pressure? Look, we don't want this graph. Look, in this point, the mole fraction of A is 1 and mole fraction of B is 0. And in this point, mole fraction of A is 0, mole fraction of B is 1. It means from this end to this end, the mole fraction of A is decreasing, and from this end to this end, the mole fraction of B is decreasing, right? So what does it mean? From here to here, I am adding mole fraction of, that is B. So at this point, when mole fraction of B is 0, it means there is no B present over here. So I am talking about this solution. Now it is completely pure form. So the vapor pressure here is going to be PA naught, right? The vapor pressure is going to be PA naught. But what happens when I add B to this? When I add B to this, what happens? The pressure due to A is going to decrease. So you can see decrease graph here. And if I talk about this graph, from here, this end to this end, I can see the mole fraction of B is decreasing. It means at this point, there is no more A present, only B is present. So the pressure due to this is going to be pure PB naught, right? So it is going to be a vapor pressure of pure B. So it is PB naught over here. So again, I'll see decreased graph. So when I combine this graph, I'll get the total vapor pressure. This is the vapor pressure of a solution after mixing component A and B. So can I write this as PT? PT means total vapor pressure, right? So this graph shows us how this liquids mixture is going to behave in terms of vapor pressure, right? So overall, after mixing, total vapor pressure, obviously it is going to be same. It is going to be equal to the partial pressure of A and B, right? Okay. Now let us see non-ideal solution. So what is non-ideal solution? So non-ideal is a reverse case of ideal solution. As I said, in non-ideal we saw AB interaction is equal to AA and BB, right? But here it is not. They won't be equal. So if they are not equal, it means they will be either higher or lower than it. So in ideal you will be having two cases here. Positive deviated one and negatively deviated. So what is this positively and negatively deviated means? Simple thing. Suppose I have liquid A and liquid B, and after mixing liquid A and liquid B, if you see the volume of it is increased. Volume is increased. Or volume is decreased. It means they are showing non-ideal behavior. If you see change in energy, then they are behaving as non-ideal solution. So let us see. So as they have written a condition, enthalpy is not equal to 0. Means you will see either energy is absorbed or liberated. You will see two conditions. Either it is absorbed or liberated. Volume won't be same. Either volume is going to increase by adding two liquids or decreases by adding two liquids. Okay. So as I said, Rolle's law shows two type of deviation. One is positive and one more is negative. Okay. So what I wrote here, AB is less than AA and BB. So interaction of AB is lesser. So if the interaction of AB is lesser, as I said, after mixing A and B, if the interaction is lesser, if the attraction between AB is lesser, it means they'll convert into vapors easily. Yes or no? Yes. Yes ma'am. They'll convert into vapor easily. So the vapor pressure increases or decreases? Obviously vapor pressure will be higher compared to A and B. Right? So as we expected from Rolle's law, it is not behaving as per Rolle's law. Now they are behaving in different way. According to Rolle's law, it says the amount of A determines the vapor pressure, right? But here it is showing a different nature. Because of its interaction, the vapor pressure is increasing. So if the interaction between AB is lesser, then the vapor pressure is going to be higher. If the interaction of AB is very much strong, if they are bonded very much strongly, then they won't convert into vapor form. If they won't convert into vapor form, the vapor pressure is going to decrease. So in positive deviation, you will see increase in vapor pressure, and in negative deviation, you will see decrease in vapor pressure. Increase in vapor pressure, decrease in vapor pressure. Let us see this in detail. Ideal solution which shows positive deviation. As I said, AB interaction is weaker. AB interaction is weaker, lesser than AA or BB. So if it is lesser, if the interaction is lesser, it means they'll convert into vapor form easily. Look, simple concept. If the attraction between them is very much lower, which is very much less, they are not attracted, they are going far away. It means they'll convert into vapor form easily. So once when they convert into vapor form easily, then the vapors are going to increase. So if the vapor is increased, it means it is not following the Rolle's law. Right? So partial vapor pressure is due to A is greater than mole fraction of it. So it is not following Rolle's law at all. So what this says, total vapor pressure is greater than what we predicted by Rolle's law. And how about volume? Right? So if they are converting into vapor form easily, then volume is also going to be greater than 0 and enthalpy is also greater than 0. And the graph is also going to change. As we saw, the vapor pressure is increased, it means the curvature is upward. It is increased, it means curvature is upward. We had this graph, right, for ideal solution. But now for positive deviation, you'll see this kind of graph, right? So deviated from Rolle's law. This shows it is not following Rolle's law at all. So we have some examples which are showing positive deviation: ethanol and water, CH2 and acetone, CaCl4 and benzene, and many more examples we have. Okay. Now let us see next non-ideal cell, negative deviation. So negative deviation, it is stronger. So AB interaction is greater, stronger than AA and BB. And again, change in volume is greater than 0. Change in enthalpy is also greater. It's less than 0. Okay. And total vapor pressure is less than sum of the vapor pressure of its components. Right. So here you will see minimum deviation. It means the slope or this curvature is downward. Curvature is downward. So here we have some examples: nitric acid and water, ethanol and acetic acid, and many more. Okay. Next comes azeotropic mixture. What is azeotropic mixture? Azeotropes are like a soulmates. Soulmate. Why I am calling them as a soulmate? Because they are unbreakable. Their bonding is like once when they become a friend, once they join their hands, they won't break. Even if you boil them, even if you do anything, they won't be separated easily. So what do we say? It's a mixture of two liquids which boils at particular temperature like pure liquid and distill over the same composition. It means they boils. Suppose I have a liquid mixture, A and B. Two liquids I have added, right? And I have supplied a lot of heat. It means they are converted into vapor form. And once they are converted into vapor form, I am undergoing distillation process also. They will convert into vapor form and again condenses and converts into liquid. Even after converting into liquid, even after undergoing this distillation, they won't change their composition at all. It means their mixture is going to be same. They are like AB. Once the A plus B you have added, they converts into AB. They acts like a single molecule, single liquid. You can't separate them in easiest possible manner, right? So such liquids are called azeotropic mixture. Okay. And here you will see two types again: minimum boiling and maximum boiling azeotropes. And minimum boiling azeotropes are generally a positively deviated liquids, and maximum are negatively deviated liquid. So we have some examples over here: ethanol and water in this proportions, they act as a minimum boiling azeotrope, and water and HCl, they are negatively deviated and they act as a maximum boiling azeotropes, right? So once again I would like to glance everything in a form of story. I said 4 cases here: ideal, ideal, non-ideal. In non-ideal we have 2 positive deviated and negatively deviated, and last one is azeotropes. Okay. So ideal solutions are, I said, they are a good kind of friends. Consider I am just comparing this different liquids with their in a form of friendship. This ideal solutions are, or ideal friends are, such a way that they won't change their volume, they won't change their energy. So the change in volume is going to be 0. Here change in volume is 0, change in enthalpy is 0, and the interaction is completely same in AB. But in positive, the interaction of AB is not same. Then in positive deviation you will see they converts into vapor form easily. It means the interaction of AB is lesser. Interaction of AB is lesser compared to A and BB, and here interaction of AB is greater compared to A and BB. And how about azeotropes? Once when they have mixed, they won't convert into, once they have mixed, they won't be separated easily. They are unbreakable bonds. It's like unbreakable bond is present over there, right? So this is all about 4 different types of liquid mixture. Now let us move on to problem part. Here we have a question. Mixture that forms maximum boiling azeotrope. Maximum boiling azeotrope. Again, just now we saw examples over here. Maximum boiling azeotrope, HCl, water, right? So let us see which is common here, given over here. So heptane and octane is ideal. Water and nitric acid is going to be answer over here. Yes, it is maximum boiling azeotrope. Ethanol and water is minimum boiling. It shows positive deviation also. And this is also minimum boiling azeotrope. So maximum boiling, B is the correct answer. Which one of the following is incorrect for ideal solution? Incorrect. They are asking incorrect, not correct. So this is correct. This we don't know. This is correct. Okay. So let us see what is delta U. Delta U is equal to delta H minus delta V. T delta V. Yeah. So if this is 0, this is 0. 0 minus 0 is going to be 0. So this is also correct. This is also correct. But how about delta G? Delta G is equal to delta H minus T delta S. But for ideal solution, do remember, for ideal solutions, delta S is not equal to 0. Delta S is not equal to 0. If delta S is not equal to 0, even if this is equal to 0, overall delta H is not equal to 0 for ideal solution. But here they give equal to 0. It means this is going to be a correct answer. Okay. For an ideal solution, the correct option is, again, for ideal solution, which is correct option here? D. We know, because enthalpy is equal to 0. This is wrong, and this is wrong. Just now we saw why it is, right? So the enthalpy is 0. The change in enthalpy is 0 for ideal solution. That is a correct option. Okay. Which of the following statement is correct regarding a solution of two component A and B exhibiting positive deviation from ideal behavior? So they are asking about positive deviation and which is the correct statement. And as we know, in positive deviation, the interaction of AB is less than AA and BB. So interaction of, so first option, intermolecular attractive force between AA and BB is stronger. It means it's greater than those of AB. So AA and BB is greater than AB. So yes, this is a correct answer, right? So positive deviation doesn't be equal to 0. It's not equal to 0. This is also not equal to 0. So they are wrong. Again, this is also wrong. So correct answer is option A. In water saturated air, mole fraction of water vapor is 0.02. So just write on the given part, mole fraction of water is 0.02. If the total pressure of saturated air is 1.2 atm, so what they have given? Total pressure. The total pressure is 1.2. The partial pressure of dry air is. So the question here is to find out partial pressure of air. And again, this is related to ideal solution only, right? But in vapor form, it's related to Rolle's law, right? Rolle's law in vapor phase. So we know that. What we know? We know the formula. That is PA is equal to mole fraction of A into P total. This is what the formula we had, right? So here if I talk about P air, the partial pressure of air, it should be equal to mole fraction of air into total pressure, total vapor pressure. But we don't have mole fraction of air for value, we have only for P total. To find out this, first we need to find out so what we will do, we are going to apply this formula over here. P water is equal to, wait, let me rub this. P water is equal to mole fraction of water into P total. Okay, now we have mole fraction of water. Let me write it down, 0.02. P total also we have 1.2. Let's solve this first. We'll get the partial vapor pressure of water. So if I multiply this, 12 2s are 24. We have 0 0. So after 3, here we have. So partial pressure of water is going to be 0.024. Now we need to find out partial pressure of air, and we know that total pressure is equal to partial pressure of air and partial pressure of water. So this is the general thing we know. Total vapor pressure is equal to sum of the partial pressure of the components, and here air and water is the two components present over here, right? So what we will do, we'll simply write down the given whatever the thing we have, data we have. 1.2 I'll write down here. P total. P air do we have? No, that is only what we need to find out, plus partial pressure of water, we got it from here, that is 0.024. Now I'm going to subtract. So when I subtract its value, 1.2 minus 0.024. So we need to subtract this. When I subtract this, I'm going to get, it's going to be 6. This is going to be 9. This converts into 1, 1, 7, 1. So the answer here is 1.176. So option C is a correct answer. 1.176. So option C is a correct answer. Okay. So thank you. Bye bye. See you in the next video.